Hey everyone, it's Ken. I'm here to tell you about L'Hopital's rule. So as I understand it, L'Hopital didn't actually invent this rule, didn't actually invent this theorem. I believe he wrote one of the very first calculus textbooks and therefore popularized it. And as is often the case in mathematics and in life, the person who popularized it got their name attached to it. I actually don't know who invented this. But what it says is, if you go back all the way to very close to the beginning of the course, one of the first things we did was try to figure out, like what's the limit of a function. And so we did like sine x over x or things like that. And we quickly discovered that some limits are harder than others because we ran into these so-called indeterminate forms. So in other words, we were taking a ratio of two functions, right, f of x and g of x. We are looking at a limit as x goes to some fixed value a, and the form was indeterminate if when we plugged in we got 0 over 0 or infinity over infinity or negative infinity over infinity or infinity over negative infinity. You can shorten that by just saying 0 over 0 or plus or minus infinity over plus or minus infinity. So those are the cases where you cannot determine the actual limit if it exists just by plugging in the number. And when that's the case, there's a nice trick that you can do to possibly help you figure out what that limit actually is. And I'll just state the rule right here and then explain it a little bit. This limit is going to be equal to the limit as x goes to a of f prime over g prime, provided that the derivatives, of course, exist. Just to be safe, I'm going to ask that the derivatives are continuous, and I'm also going to ask that g prime of a is not equal to 0. But under those conditions, then this equation will be true. And let me just briefly talk about why this might make sense for it to be true. The actual proof is not super easy. It's a theorem of real analysis. But the intuition is, if you're looking at a ratio of functions and say that they're both going to infinity, so say that you have that kind of indeterminate form, then if the limit is actually equal to a number, like 1 or 2 or 3, then that's telling you that the top function is going to infinity twice as fast as the bottom function. So that's limits kind of telling you how fast one is going to infinity versus the other one. And if you're hoping to get information like that, it makes sense that you might look at the rate of change of the individual functions. So looking at the ratio of the rates of change should give you information about how fast one's going to infinity relative to the other one. So at least that's some intuition that makes sense. Here in this video, I really just want to show you how to use this rule in a couple of examples. And so the first example, let's try to pick something simple. Let's take f of x equals x minus 1 squared. Let's take g of x equals x minus 1. And let's take the limit as x goes to 1, so a equals to 1. And this is an example that you can figure out without L'Hopital's rule. You can just cancel out one factor of x minus 1. You'll be taking the limit of x minus 1 as x goes to 1. You'll know that's equal to 0. But let's verify that L'Hopital's rule is true by applying it anyway, trying to get the right answer. So when I do that, I take the derivative of the numerator to get 2 times x minus 1. Take the derivative of the denominator to get 1. And now when I do this, when I plug in, now it's no longer undetermined, so I can plug in and I'll get 2 times 1 minus 1 equals 0. So L'Hopital's rule verified for me something that I knew already, that this limit was equal to 0. And let's do another example. Let's take something like x squared plus 1 over 2x plus 1. Let's take the limit as x goes to 1. So can you use L'Hopital's rule for this? If you do, try to use L'Hopital's rule. Let's see what happens. I'm going to take the derivative of x squared plus 1 to get 2x. And then I'm going to take the derivative of 2x plus 1 to get the number 2. And so the limit as x goes to 1 of 2x over 2, that's just the limit of x as x goes to 1. So that's just equal to 1. On the other hand, let me calculate this directly by just plugging in the number 1. So here I'm going to get 1 squared plus 1 equals 2, and here I'm going to get 2 times 1 plus 1 equals 2 plus 1 equals 2/3. So you see I've calculated this limit 2 different ways, and I got 2 answers. So something has to be wrong. So it turns out that this top one is wrong. This is actually the right answer. The reason why L'Hopital's rule didn't work here is because this is not an indeterminate form. This does not give me 0 over 0 or infinity over infinity when I plug in x equals 1. And in fact, L'Hopital's rule tries to give you an answer when you do the process, but that answer is incorrect. L'Hopital's rule will potentially give you an incorrect answer if you don't verify that you're starting with an indeterminate form. So make sure that you look out for that. Let me try one more example. Here's an example I really like. So say that we take the limit x goes to 0, x times natural log of x. So I just gave you a warning about verifying that it's in an indeterminate form. So can you use L'Hopital's rule for this? At first it seems like there's no way you could do it because it's not even a fraction. It's not expressed as f over g. But you can re-express it. So you can rewrite this. This is kind of nice. You can rewrite this as natural log of x over 1 over x, because x is certainly equal to 1 over x, right? Okay, so when I do this, I can verify that this is now an indeterminate form, because when I plug in 0 or take the limit as x goes to 0, then natural log of x is going to negative infinity. And here, as I take the limit as x goes to 0, I'm getting plus infinity from the right and negative infinity from the left. And actually, since the domain of natural log of x is positive real numbers anyway, should probably be taking this limit from the right. And L'Hopital's rule works with one-sided limits as well as usual limits, so that's no problem. So when I actually apply L'Hopital's rule to this, I take the derivative of natural log to get 1 over x. I take the derivative of 1 over x to get minus 1 over x squared. And now I've got a little bit of algebra to do. So I can actually cancel out a factor of 1 over x to get 1 over minus 1 over x. And coming down here, that's going to give me limit x goes to 0 from the right. And 1 over minus 1 over x is just minus x. And so you can now see quite clearly that this limit of minus x as x goes to 0 from the right is just going to be 0. Certainly minus x goes to 0 as x goes to 0. And so what this is telling us is that this limit is equal to 0. And so what this is telling us intuitively is that x goes to 0 faster than natural log of x goes to negative infinity, right? Because when you multiply them together, that quantity, that multiplied quantity, goes to 0. Even though natural log was trying to push you down to negative infinity, x takes you to 0 faster than natural law can do that. So that's one way we like to conceive of limits like this.